Souhaiter la bienvenue à cet événement annuel qui est la remise du prix Justine Yves Sergent. Vous m'entendez bien? Ça va? Alors, mon nom est Yves Joannette et je suis responsable du fonds Justine Yves Sergent. Et à ce titre, il me fait plaisir de vous introduire un peu le prix Justine Yves Sergent avant d'introduire la lauréate de cette année. Est-ce que... Voilà. So I will switch to English and remind you that the Justine and Yves Sergent Fund was endowed at the Université de Montréal in 1998, so the last millennium, by the Sergent family and Mrs. Edith Laubier. The family was in fact the mother of Yves Sergent, and unfortunately deceased some years ago, but she was there and very proactive in making sure that there would be such a fund and such an award. And the fund was exceptionally supported by Mrs. Edith Laubier, who was not a researcher, but who was someone who was supporting lots of things in Montreal, including research, but also the association, making sure that the mountain of Montreal would still be a mountain, and so on and so on. So she and her husband invested a lot. She had the Order of Canada in 96. She had a honoris causa doctorate from Université de Montréal in 2009. And she was, and she's still an honorary member of both the Department of Psychiatry at McGill and the Faculty of Medicine at Université de Montréal. Unfortunately, also deceased some years ago. The fund was created to the memory of Justine and Yves Sergent, who both passed away on April 12th, 1994, in the context of, unfortunately, of a long-standing, profound misunderstanding, including allegation of ethical misconduct, for which an inquiry was suspended 3 years after her death without having raised any evidence. So Justine Sergent was in fact born in Lebanon. She was a primary school teacher in Lebanon. And in Lebanon, she met Yves Sergent, who was from France and was in Lebanon because of some role in a military role from France in Lebanon. And rapidly they came back to Paris. And Yves Sergent became also rapidly psychopedagogue in a school in Montreal. And that's why Justine Sergent came to Montreal. And the first year and a half or 2 years, Justine Sergent was in Montreal. She was a primary school teacher as well in the English school system in Montreal. And of course, after she became a researcher and so on, and she was also, both of them were loved music, and you'll see why I mentioned this later on. And so they were very close together, had no family here. And that's why they were very, very close, and that's why they decided the end of them in a certain point in time. Just to mention that Justine Sergent did a lot of work on split brain patient at that time, and she introduced the concept that the two hemispheres are integrated. There's no asymmetry between the hemispheres. And that's something that they are coordinating. That's something that was very important at that point in time. She also worked on face and object processing with neuroimaging using a PET scan to do the first neuroimaging study of face perception. She did also the first study published in Science about the musical reading and keyboard performance. So she was really someone very known in the world for her 10 years. And this is the last, unfortunately, I'm sharing with you because her mother-in-law is always asked me to share that last sentence that Justine, the day they passed away, wrote that I had a rich and intense life, but there comes a point when one can no longer fight and one needs a rest. So it is this rest that my husband, who has supported me in all aspects of my activities in my life, and myself have decided to take. And this was their last sentence. But the Justine Yves Sergent Award honor a woman-born researcher who has developed an international reputation in the field of cognitive neuroscience and brain imaging. The management committee includes the Vice-Dean Research Ecat Criticu, and also here Simona Brambati. I'm sorry, I don't have the right slide here, Simona, so thank you for being here. And the scientific committee is composed of Dr. R.G. Illis from Johns Hopkins, Rita Hari from Finland, Cheryl Grady from Toronto, and the scientific committee looks at the world and identify each year who could be the best person to recognize. The first person in 1999 was Leslie Ungerleider, and over the last 5 years, from 2020, sorry if it is there is an error here, it's 2020. Maria Luisa Gorno-Tempini from California was awardee. Nancy Kenwisher in 21, Heidi Johansenberg from Oxford in 22, Katrin Hamunz from Germany in 23. Last year in 24 was Aude Oliva from MIT, who received the award while we were celebrating the 25th anniversary of the fund. And this year, we're celebrating the 26th anniversary of the fund by recognizing, according to the scientific committee, that Professor Dani Bassett, who's G. Peter Skirkanich Professor at the University of Pennsylvania, is the 2026 awardee. So Professor Bassett is most well known for blending neural and system engineering to identify fundamental mechanisms of cognition and diseases in human brain networks. Professor Bassett is at the University of Pennsylvania, and just to express how interdisciplinary and transsectorial Professor Bassett is with appointments in the departments of bioengineering, electrical and systems engineering, physics and astronomy, neurology, psychiatry. Maybe I'm forgetting some, but these are really impressive. Professor Bassett is the author of 480 peer-reviewed publications. This was yesterday, maybe today is more. Including a recent MIT Press book titled Curious Mind, The Power of Connection, with philosopher and twin Perry Zurn. Professor Bassett received multiple prestigious awards, such as the Alfred Sloan Research Fellow, the MacArthur Fellow, Genius Grant, Lagrange Prize in Complex System Science, Erdos Reni Prize in Network Science, and an American Physical Society Fellow. So it is with a great pleasure that we are welcoming Professor Bassett, who will be sharing with us the Justine Yves Sergent Conference for 2026, and after we'll receive the award from the Faculty of Medicine. Professor Bassett, I'll give you the microphone.
Thank you very much for that introduction. I'm very honored to be a laureate for this award and to follow in the footsteps of Justine. I also want to recognize the openness of the committee and the fund to offer this award to someone assigned female at birth, but in a gender inclusive way. I identify as trans and non-binary, so I don't identify as either a woman or a man. but I appreciate the fact that this is an award that is for individuals who were born like me, independent of how they live the rest of their lives. So today what I'd like to do is to talk about network cognition in a curious world. The story that I want to tell is intertwined in 3 parts. I want to start with how the body seeks information in the world. Then I want to move into how the mind builds models of the world. And then lastly, I'll turn to the brain and ask how it transduces the information in the world to produce these models. What I'll be doing then in the first part is really focusing on curiosity. How do we seek information in the world? And I'll focus on experiment and support it with some theory and models. In the second section, where I talk about how the mind builds models, I'll be focusing more on learning. And I'll foreground computational modeling with the support of experiment and theory. And in the last section, when I turn to the brain, I'll be talking more about control and how control theory and as a way of thinking about how the brain transduces information in the world around us. So let's start with the first part on curiosity. What is curiosity? The traditional view of curiosity is that it is both acquisitional, we acquire a piece of information, and it's also individual. A single person seeks out that information. The typical neurological experiments or neuroscience experiments around curiosity tend to be of this sort of ilk, where people's curiosity is focused on seeing a clear version of a distorted image, or it's focused on finding a piece of trivia, or it's focused on the love of something novel or neophilia. But all of these are focused on a single person identifying a piece of information. And I want to ask, is this view comprehensive of the ways that humans experience curiosity in their everyday lives, or is there something more? I think there's something more, and I think it is something that can be clarified using an alternative definition of curiosity that's explicitly relational. Yes. Oh, thank you. That explicitly relational definition of curiosity has a hidden history. We can go back multiple centuries, for example, to 1531, where we hear that with curiosity, some things follow from the findings of others. Just as when the beginning of a thread is secured, it is found to be connected with another set of things, quite different from those which were originally imagined or examined. So what they're talking about here is that curiosity is the following of a thread. You are interested in something because it's connected to something else, which is connected to something else. Similarly, if we fast forward to Charles Sanders Peirce, curiosity is described as stimulated by the rational relations between things. So it's not that it's necessarily stimulated by independent floating pieces of information. What's stimulating, what's motivating to us is how those pieces relate to other things that we know. And then if we fast forward to John Dewey in 1916, he writes that knowledge, all of knowledge, so this is a rather large claim, knowledge is a perception of those connections of an object which determine its applicability in a given situation. And ideally, perfect knowledge would represent such a network of interconnections that any past experience would offer a point of advantage from which to get at the problems presented in a new experience. So what he's saying here is that knowledge itself is a network of interconnections. And that's important because that's how that's necessary for us to use the information for a future decision. So how does this relational curiosity show up in human lives? Well, one way that we can address that question is by looking back over historical periods. This is work that was done by my twin, Barry Zern, who's a philosopher, and he went back over the last 2,000 years and focused on writings in the Western intellectual tradition. And he identified the terms for curiosity in Greek, in Latin, in French, in German, and in English. And he also looked at synonymous phrases. In doing so, what he found is that curiosity is described relationally, specifically in 3 different ways. The first is what's commonly described in older literature as a busybody. That has a negative connotation today, but you can think about it more as a social butterfly in an epistemic space, loving to flip between different pieces of knowledge. So the busybody is somebody who seeks these discrete pieces of information and builds relatively loose knowledge networks. By contrast, the hunter, which is another style that's consistently described over these 2,000 years, is one who focuses on targeted connections, follows a trail, sniffs out something, is really focused on following that thread that we just described previously. And the third way that curious people are described in this literature is as dancers, people who leap between one piece of information and another piece and stitch them together as if they were choreographing some epistemic object. And those individuals will create more stringy knowledge networks. So the question for me as a scientist is, can we see these same styles of humans, or these same styles of curiosity in humans today? And that is work that was led by David Lyden-Staley when he was a postdoc in my laboratory. He had 149 participants volunteer for a study where they were browsing Wikipedia for 15 minutes a day for 21 days, so 3 weeks. Over the course of that study, we tracked which Wikipedia pages they went to and how they transitioned and when they transitioned between them. Our hypothesis was that we would see people who are more like hunters, those that are following a trail and going between Wikipedia pages that are really similar, and then other people who are more like the busybody, going back between pages that are relatively dissimilar to one another. We also hypothesized that that difference between people who are more busybody-like and more hunter-like would be explained by a personality trait known as deprivation sensitivity. Someone who is high on deprivation sensitivity would say, yes, it frustrates me not having all of the information I need. If it doesn't frustrate you so much not having that information, then you would be low on deprivation sensitivity, and we would hypothesize you would browse more like the busybody. So let's see what he found. This is the first piece of data from that study that I wanted to show you. And what you can see here is a correlation between individuals' deprivation sensitivity on the x-axis and the clustering coefficient of the networks that they are constructing. That's related to how densely or similarly related the Wikipedia pages are to one another that they're flowing among. So what you can see is a positive relationship here. The hunters are over here on the right-hand side, building networks with high clustering, following that thread. And those individuals are high on deprivation sensitivity. It bothers them when they don't know something. The individuals over here on the left-hand side, the busybodies, they create networks with lower clustering coefficient, so more stringy structures. And those individuals are not as bothered by not having the information they need. Importantly, we also found that individual levels of depression and anxiety were associated with these tendencies, specifically that those individuals who have higher levels of depression and anxiety take shorter steps on the Wikipedia network and go between pages that are more similar to one another. Now, the next question we had was, how does this simple finding from 149 participants in the laboratory generalize to a much larger cohort? To address that question, we collaborated with Martin Gerlach, who is a senior research scientist at the Wikimedia Foundation. And he provided us with data from over 2 million users of the Wiki mobile app. So we have browsing data from 50 countries and 14 different languages of Wikipedia. We subsampled that data to a little over 400,000 individuals so that we could match our laboratory data and the mobile data on the number of page views, or basically the size of the network that people were browsing. And what we found is that we could clearly see people who were more hunter-like and people who were more busybody-like. What you're seeing here on the bottom is the busybody hunter score. So if this is larger, then the individual is more hunter-like. And if this is lower, the individual is more busybody-like. In blue, you see the naturalistic data. In orange is the laboratory data. You can see that those two curves lie very close to one another. By contrast, the green curve is when you place an agent on the Wikipedia network and let it walk randomly along hyperlinks. You can see that if you do that, the random walker will move locally because it's following the hyperlinks, whereas individuals tend to browse a little bit more further away. So what this indicates to us is that the browsing patterns of the naturalistic data and the laboratory data are in line with one another. There's a generalization across these two studies, and both are significantly different from a random walker. We also found that busybodies tend to browse a diversity of topics. So along the y-axis here is topic diversity, and along the x-axis is the network structure, from more busybody-like to more hunter-like. You see a negative relationship here, so that means that the busybodies are browsing with higher topic diversity, and the hunters are browsing with less topic diversity. We also find that this difference varies across countries. I told you that this was data from 50 different countries, right? So it varies across countries in a way that maps onto well-being and onto measures of social inequality. So here what you're seeing is that there's a correlation between the degree of browsing more like a hunter and negative affect in that country overall. It's also correlated with gender inequality and with education inequality. By contrast, those who browse, countries that have browsers who are more like busybodies tend to have more positive affect and more gender and education equality. This relationship between the way that people are browsing and these overall markers of equality and well-being across 50 countries could be driven by a variety of factors, and we're not sure yet which one. That's going to require us to do a little bit more digging. But some of the factors that might be important are first patriarchal forces that could be driving a constraining of knowledge production approaches and leading to a more hunter-like curiosity consistently across individuals. Another potential explanation is that browsers in different countries have a different demographic composition. They could be different ages, they could have different socioeconomic status, they could have different gender, they could have a variety of differences that could change the way that they're browsing. And third, browsers in different countries may have different motivations for turning to Wikipedia. In some countries, people may be coming for work, whereas in other countries, they may be coming for play or for entertainment, or from boredom, perhaps. So we're digging into that a little bit deeper now, but meanwhile, we also wanted to ask how we could use this understanding of relational curiosity in humans to inform artificial intelligence. What we can do is that we can build artificial agents that will construct knowledge networks that are more like busybodies or more like hunters. And we do that by using a novel reinforcement learning approach wherein the edges in the network are valued according to how they change the network topology. Do they make it more clustered or do they make it more stringy and expansive? In this way, we're able to construct something that is both task agnostic and content agnostic, and therefore importantly is detached from the local semantics of the environment. When we create these artificial agents, we can show that they can be used to better predict exploratory human behavior in the Wikipedia game, in movie lens, so how we move from movie to movie in our everyday lives, and how people move from book to book in Amazon Books. We're able to better predict their behavior than using a simple PageRank algorithm. So that suggests to us that there's something important about these characteristics of relational curiosity that explain human behavior and can be implemented in artificial agents. The next steps here are to assess whether relational curiosity is a driver of what's known as meta learning or learning how to learn, because it provides this task agnostic and content agnostic programming. With that, what I'd like to do is to move to the second part of the talk, where I want to ask not just how we engage curiously in the world around us, but when we do that and when we receive information from the world, how does our mind build models of that information? So here I'm going to focus on a computational model, but first I'll show you some of the data. So in this area of the research in my lab, what we do is think about how we engage in the world, how we engage with language networks, how we engage with social networks, how we engage with music, how we engage with lots of different relational objects in the world around us, and then how we build models of those relational objects. So how do humans do this? One of the ways that humans do this is using what's known as statistical learning. So we're receiving a stream of information from the world around us, and slowly over time, we build up predictions of transition probabilities. How probable is it that I'll transition from this word to this other word, or from this moment in a musical composition to another moment in a musical composition? This capacity that we as humans have to infer pairwise dependencies from incoming streams of data allows us to do many things, including learn language, or segment visual events, or infer social networks, or perceive distinct concepts. So how do we understand how people are actually building these models? One of the ways that we can do that is by constructing data that looks like the world. So we can define a network, which is what I'm showing you here on the bottom, and we can let every node in the network be a word or an image or a movement or some item that we might be exposed to. And then we can let every edge in that network be a transition, an allowable transition between those items. Then what we can do is we can take a walk on that network, like a random walk, and show individuals the stream of information that would come from taking a random walk on the network that we've defined. As we do that, we can assess how well they're learning the network and how well they're building a model by asking them to perform a small task such that we can measure their reaction time. If they react swiftly to that small task, it means they've learned that transition in the network and that local structure in the network. If they respond very slowly, that means that they haven't yet learned that piece of the network very well. Now, before I show you our data, I want to tell you about a well-known fact about this kind of experiment. And that well-known fact is that when humans are exposed to a piece of the network where there's only one possible outcome from it, there's ultimate certainty. They know exactly what's going to come next because there's only ever one option out of that node. And so they'll respond very swiftly because they know they're ready. They know what to prepare. By contrast, if they're sitting at a place in the network like this with 14 possible outcomes, they'll respond very slowly because there's a lot of uncertainty about what might be coming next. So there's a strong correlation, or should be, between the swiftness of people's responses and the local complexity of the environment. So we are just showing in our data that we can reproduce that fundamental effect that's pretty well known. So here along the x-axis is the entropy, the local entropy of that spot in the environment. So how many edges are coming out of a node? How many possible transitions could somebody face? And then along the y-axis here is the reaction time. What you can see is a strong positive correlation between these two variables, such that humans respond slower when there's a lot of local entropy, many possible outcomes, and they respond faster when there's very little entropy. They know exactly what's coming next. Now, what we were curious about is whether humans just learned this local entropy or if they're learning something else about the network structures around them. And my graduate student, Ari Khan, showed in 3 different ways that humans are sensing something more about the network than just the local environment. So one of the things that they're sensing, I'll have you focus on the left-hand side of this slide, they're sensing boundaries between sectors of the network. We can see that because there's a striking slowing. Their reaction time slows significantly when we show them a transition that crosses between different clusters or different modules in a network. So that suggests to us that even though the local structure in these environments is the same, every node in this network has exactly 4 edges. So the local structure is flat, right? But people are sensing more than the local structure, and they're slowing down when they cross these cross-cluster boundaries. So then we thought, well, maybe they're performing something like category learning. They're just detecting that there are 3 categories here, and they're separating them in their minds. But we don't think that that's actually what's happening because we can see a graded change in their reaction time according to where they are in the network. So here what you can see is that they're fastest in these internal, this internal capsule, this internal triangle. They're middling fast at the purple edges, and then they're slowest at the cross-cluster edges. So there's a change, a graded change in their reaction time according to where they are in the hierarchy of the network. And lastly, what we found is that they are sensitive to the global topology of the graph. So if we look at 3 different networks and all of them have identical local structure, so every node has exactly 4 edges in each of these networks. The local structure is exactly the same. We observe that humans are swiftest in responding to information presented on the modular graph. They're less swift at responding to information on a lattice graph, and then they're slowest responding to information on the random graph. So what that means is that they're sensing something about the global structure, even though the local structure is identical. So what could be happening in the human mind that allows us to sense not just local structure, but also mesoscale structure and global structure? And this is work that was led by Chris Lynn. What he posited is that when the human mind is building network models of the world, it has to arbitrate a trade-off between building a model with high complexity and perfect accuracy, or building a model with less complexity and a lot of inaccuracy. And we tend to find models, we tend to choose models in between. So we get as much accuracy as we can for as little computational resources as we can. We can formalize that in a free energy model that balances the probability of having errors in your memory of what happened a moment ago and entropy in your model of the world. The image that I'm showing you here is when a person has perfect memory. They remember every single previous stimuli in the past that they've seen in this stream, but they're maximizing the mental resources required to build that model. They come up with a model that's perfect, but we know the humans aren't doing this because they are slowing at the cross-cluster boundary, they're responding differently to different networks, and they have this hierarchical gradation in their responses. So they're not doing this. What they're doing is something a little bit more like this, where there's a little bit of imperfection in the memory, such that they don't remember exactly what they saw a moment ago. Maybe they were distracted by a fly on the wall or thinking about dinner. So they actually remember something that happened 2 moments ago. So they build an expectation in their mind between the item 2 moments ago and the item now. What that does is that it adds these extra edges that I'm showing you here in gray. Right? So it makes everything a little bit fuzzier. It adds edges they didn't see, and that allows them to create something that's close to accurate, but not exactly accurate. But also allows for us to be forgiving of our own imperfections in attention. Okay, so why is this model important? Well, it's important because it accurately fits the human data that we have acquired, especially in the vicinity of this beta around 1. But it's also important because it helps us to predict human responses in a new context. So from this model, we can show someone a new graph, and we can predict how their reaction times will vary according to the topology. But the third, and I think the most important thing that this model adds, is that it provides us with a deeper understanding of how much information we actually perceive in our environment. What do I mean by that? Well, what I mean is that when we are exposed to information in the world, we're exposed to something like this, right, that has some particular structure, but what we actually learn is something that diverges from that. And so then when we're engaging in the world around us, we're facing this additive complexity where we have to learn, we're processing the complexity of the actual network, but we're also processing how different our expectations are, our imperfect our expectations are from the world. So there's these two pieces that are coming in at us as we're building our models. So we can quantify these two separate pieces. The first one is just the entropy of the system that we're being exposed to. And then the second one, how distinct our expectations are from the truth, we can quantify using what's called KL divergence. So I want to show you those two quantifications measured in real information systems that we engage in everyday life. So these information systems come from language, so word transitions in books. They come from semantic relationships. They come from the structure of the World Wide Web or the internet. They come from citation patterns, from social networks, and also from music, where we study note transitions in both classical and modern pieces. What you can see here is that these systems have very high entropy. They're complicated. They have complex network structures or transition structures. And the way that you can see that is along the x-axis here is the entropy of the real system, and then along the y-axis is the entropy of a random system of the same size. The gray dashed line is the identity line, and what I want you to see is that the data points lie below the identity line. What that means is that these systems that we engage in everyday life have more entropy than is expected in a random network of the same size. But what's really interesting is not just that they're complex. We kind of know that language is complex and music is complex. But what's more interesting is that they have very low KL divergence. What that means is that they are largely forgiving of imperfections in our memories. So they have topological structures that are forgiving of those imperfections. Let me show you this data. So on the x-axis here is the KL divergence of the real networks, and then along the y-axis is the KL divergence of a random network of the same size. The gray dashed line is the unity line, and what I want you to see is that the data points lie above the unity line. What that means is that these networks have less KL divergence than expected in a random network of the same size. That means they're more forgiving of our imperfections. They will diverge less. Our expectations will diverge diverge less from the truth, and they will be therefore more easily learnable because there's less additional processing cost of this separation between our expectations and the truth. So our next question after we saw this was, why is this happening? And can we see this kind of ease of learning networks with high entropy and low KL divergence in the brain? What we did first computationally is just to demonstrate that networks that do this, that have high entropy and low KL divergence, are modular networks. They're consistently hierarchically modular networks. So we thought, well, let's go into the brain and let's ask, are these modular networks differently encoded in the brain in a way that allows us to understand why they're more easily learnable? So we have a human participant in this experiment. We have them look at information that's taken from a network model of the world. We look inside of their brain, and then we ask, are the representations of those networks clearer and more efficient and more predictable when we see information from a modular graph? Now, we already know from previous work by Mona Gavert that there is a system in the brain that tracks the network structure of the world that we're exposed to. That's the hippocampal entorhinal system, which can encode two things about the networks we're exposed to. It encodes the distance between different nodes in the network, and it also encodes whether two items in a network are connected or not connected. So we already know that the brain is encoding this structure. And now our question is it encoding modular structures differently from non-modular structures? This is work that was led by Ari Khan, again, and what he did is that he said, well, I'd like to ask if we have participants receive information, streams of information that are taken from a modular graph, could we then go back and look at the fMRI activation patterns and predict what they had seen? If we can do that well, great. If we can do it well from when they've seen information from a modular graph, more so than when they see information on a lattice graph, then that would provide evidence that the brain is processing these two topologies differently. So that's exactly what he found. So along the y-axis here is how well he could accurately classify what somebody saw from their fMRI activation patterns. And then along the x-axis is the area in the brain. These are from the lateral occipital cortex because they're seeing shapes. So we see this in the left lateral occipital cortex, right lateral occipital cortex, and bilateral. What you can consistently see is that the blue bar graphs are higher than the orange ones, demonstrating that participants have clearer representations of items that were presented on the modular graph than items that were presented on the lattice graph. They're the same items, though. So there's something about the topology of how you're being presented with the information that changes how cleanly you encode it. Now, this provides some biological or neural explanation for the theoretical observation I mentioned earlier that modular graphs are more easily learnable. Now, if modular networks are more easily learnable, then I think that has important implications for communication, for teaching, and for pedagogy. So some early work that we did in relation to this is to study the presentation of concepts in college-level textbooks and ask how modular that presentation is. If we look at every word in a textbook, every single word from a PDF of a textbook, and we construct a transition probability matrix from those words, then we can ask how modular is that organization or how non-modular. So this is work from Nico Christensen. It was published in 2020. And what we were able to see is that there are very strikingly different network topologies in different textbooks that are correlated with, importantly, their ratings on Goodreads. So how much the student actually liked the textbook depends very precisely on the network topology of how information was presented. We also followed that up with a study with Billy, who is now a graduate student at Harvard. He was a undergraduate at the time. and this came out in 2020. What he did was he asked, if humans learn some network structures better than others, then how can we provide information to students in a way, or humans, in a way that's maximally learnable? So if we want to present information that has a modular structure, but we know people are learning this biased version of the modular structure, is there a way for us to change how we present the material or emphasize certain pieces of the network so that what they actually learn is closer to the truth? Basically, how can we overcome the biases of imperfect memory? And one of the answers that he found is that we can reinforce these within cluster edges, and that helps increase the learnability of modular networks. Okay, so with that, what I'd like to do is to move into the third and final section of the talk. So we started with curiosity, a strand of work in the lab that's focused on how we engage with information in the world around us. Then we moved into learning. That's a strand of the lab that's focused on how we build mental models of information in the world around us. And now what I want to do is to move into the brain and ask more about what's happening inside there that allows for us to build these models. So let's think again about the human being exposed to network information in the world around us. In this process of world experiencing and model building, the human brain must move through distinct and adaptive states of activity. So I think about these states of activity as what I'm showing over here, where there's a vector, let's say, of activation across different neural units. Those could be regions of the brain. They could be neural ensembles. They could be individual neurons if you're using a non-human model. And those states change over the time, those states of activation. What I'm curious about is, as the brain is moving through these states and needs to do so adaptively to learn from the environment, how does that activity flow get orchestrated when there's a single fixed routing system, which is the structural connections between brain regions? So these large bundles of white matter tracks that allow different regions to be connected to one another. Activity has to flow through those white matter connections, and those are fixed. So how does the brain orchestrate these changes in activity profiles? The importance of the underlying network for understanding how those states are changing, I'm hoping I can show you through a really simple toy example. So what you can see here is a network structure on the left-hand side, which is a modular structure, 2 modules with 1 link in between. The state that I would like that network to reach has high activation of the first 5 units, less activation of the second 5 units. And what I'd really like to do is to have this network move from the activation profile on the left to the activation profile on the right. So where anything that was off initially is now on, and anything that was on initially is now off. Because this is a modular network, we can take advantage of that underlying network structure that provides an isolation or segregation between the activity profiles. So to make this transition, we just inject an inhibitory signal into the first module and an excitatory signal into the second module. And because they're topologically segregated, very little flow happens between them. Now I want to contrast that with a different, more difficult example. So here, notice that the network structure is the same. It's still a modular network with 2 modules and 1 link in between. But now I want it to move from an activation profile that's binary, on, off, on, off, on, off, on, off, to the opposite activation profile, where anything that was on initially is now off, and anything that was off initially is now on. There is nothing about the network topology that helps us with this problem. We have to fight every edge in that network in order to allow this transition to happen. And by fight it, what I mean is that we have to inject an excitatory or inhibitory signal into every single element in the network in order to force this thing to happen. There's nothing, we can't take advantage of what's going on underneath. So this is a simple illustration of the fact that the network structure determines the ease or difficulty of a state transition, a change in the activation profile of neural systems. And when I say it's an easy transition, it means there are fewer control signals needed, they can be injected into fewer spots, and they can extend for less time. When I say that a transition is difficult, what I mean is that there are more control signals needed across a wider spatial extent, and perhaps for a longer period of time. So how can we formalize the intuition that I'm trying to build for you here in this toy example? We can do that using what's called network control theory, which is a branch of systems engineering that has typically been applied to the study of the power grid, mechanical systems, air traffic control systems, and robotics. What's really neat about this theory is that it provides a way for us to determine which state transitions are hard given the other underlying network, and more importantly, what control signals need to be injected into the system to allow a state transition to happen. Where do we need to put them? How long do we need to put them there? Etc. So we can do that by how do we take those ideas and implement them in studying a neural system like the human brain? We can do that by starting with a model of how activity flows through the system. So here is a simple model where the state of the brain, x, at time t plus 1, is going to be equal to the state at the previous time step, but allowing activity to flow through A, which is the brain network. That's the pattern of structural connections or white matter connections between different brain regions. So if you just focus on this piece of the equation, what it says is that what happens next depends on what happened just before and where that activity could flow in the network. And that's all it depends on. Now, the third piece of this over here on the right-hand side is the control signal. So U is the control input that's injected into a specific set of regions, kappa regions, at particular times t. And beta is a matrix, usually with ones along the diagonal that indicate where control inputs are being injected. By using this formalism, what we can do is that we can estimate how much energy is, or the squared inputs here, are required to push the brain from one state to another, given its structural network. That also allows us to ask if different people have different structural networks, or if structural networks change over development, over age, or in other contexts, then how much energy is now required for these same state transitions. So when we do that, what we're doing is that we're implementing a simulation where we know that the brain exists in one particular state. Maybe we measure that with fMRI or EEG or electrocorticography or magnetoencephalography. And what we want to know is how much energy is required to get it to a different state. Here, let's say activation of the visual cortex, rather than where it would typically go. So we can estimate what control inputs are needed into which regions of the brain, and then how much energy is required to do that. Notably, this control energy that I am measuring here, we have also found that it is correlated with glucose metabolism as measured by PET imaging. So that suggests that there's a biophysical correlate or biophysical underpinning for the theoretical notion of energy that I'm talking about. So that's exciting. I think there's more work to do there, but it does give us some initial indications that while this is a theoretical notion that we calculate using a theory, it is also related to the metabolic energy that the brain is using. So let's use this idea to think about how the brain reaches novel states. If we start this whole, I started this whole talk about curiosity and seeking out information in the world around us. In order to do that, we need to be able to bring our minds to novel and new states. So I want to ask, and so did Leon, are transitions to more novel brain states more energetically costly? Does it cost a lot for us to do that? Whereas transitions to more common states, perhaps, are less costly. So to answer that question, Leon looked at fMRI data from 596 Human Connectome Project subjects. And then along the y-axis here is the control energy to reach that particular state of fMRI activation across a range of different tasks: an emotion processing task, a gambling task, language processing task, a motor task, a relational task, social task, and a working memory task. Along the x-axis, importantly, is what's called the information state of that, or the information content of that state. That is high when it's a rare state. So over here, these are very rare states, and over here, these are very frequent states. So what you can see is that when there is a rare state, it requires a lot of control energy, and when there is a frequent state, it requires less control energy. So that suggests to us that what happens in most states that the brain goes to across a variety of tasks tasks is that those states are closely aligned with the network structure underneath. So it requires very little energy to get there. And when you have to move to a state that is more rare, those are energetically costly and they're misaligned with the network. You have to activate less connected regions of the brain and deactivate more connected regions of the brain. So it's that misalignment that requires energy. As soon as the brain comes back into alignment, where the activity profile is aligned with the underlying structure, that state requires less energy. Okay, so the last piece of data that I wanted to show you, and then I'm going to broaden back out, is not just does control energy explain the difficulty of reaching novel states, but also does it explain the difficulty of reaching cognitively demanding states. So to answer this question, we need to have a task that moves people between a less cognitively demanding condition and a more cognitively demanding condition. Erzbrand did this when he was visiting postdoc in my laboratory by watching having individuals perform a 0-back attention task and then transition to a 2-back working memory task. So the first one is relatively simple and does not have a lot of cognitive demands. And then the second one is more complicated. You have to remember 2 stimuli that occurred 2 moments ago. So as they're transitioning between a 0-back condition and a 2-back condition, we can quantify how much energy was required for those transitions. So we have each of their structural connectivity matrices. We also have each of their activation profiles using fMRI. And from those, we can estimate this control energy as people move from the 0-back condition to the 2-back, and then from the 2-back to the 0-back. This is a significant increase here, such that when participants are moving from the less demanding condition to the more demanding condition, they have to exert more control energy. And when they're moving back down to the less demanding condition, they use less control energy. So this suggests that the control energy is aligned with the cognitive demands of the task. We can also ask, how much energy did it take for participants to stay in one task? If you want to hold your attention in the 0-back task for the full period of time, how much energy does that take to hold that activation profile? Or similarly, in the 2-back condition, how much energy does it take to hold you there for a period of time? That's what we're measuring over here on the right-hand side as the stability. A state is more stable if it requires less energy to hold, and it's less stable if it requires more energy to hold. So here you can see that the stability of the 0-back condition is significantly higher than the stability of the 2-back condition. What that means is that the 2-back condition requires more energy to hold, and that's because it's misaligned with the structure, whereas the 0-back condition is more aligned with the structure. We also noticed that individual variability in that 2-back stability measure was correlated with task accuracy. So for those individuals who had structural connectivity profiles and activation patterns that were more aligned with the structure when they're doing the 2-back task, they tended to perform the task more accurately, providing some behavioral relevance for these data. So collectively then, across these studies, what we've seen is that the brain's structural network constrains the flow of activity, thereby influencing potential accessible trajectories. I also noted that network control theory models those constraints and provides an estimate of the energy required for brain state transitions. I mentioned that control energy is greater to reach rare, more novel, and more cognitively demanding states. And then what seems natural for me to ask at this point is, how might this constraint determine the encoding of network elements in the world around us and potentially influence our capacity to build network models of the world? Those are questions that I have to save for another day because we don't know the answer yet. But to come back out, what we've done now over the last few minutes is focused on curiosity and then learning and then control, foregrounding the body and the mind and the brain. But you might still ask, why did I title this talk Network Cognition in a Curious World? And I think I did that because I think about the world around us as composed of a network of events, of objects, of bits of information that we experience. And then we, as we experience it, build network models of those experiences using our relatively imperfect minds. And then the model building process is supported and constrained by the brain's connective architecture. So there are network constructs at each of these levels. And in order to understand cognition, I think we have to embrace the fact that there's this network complexity at 3 different scales. So with that, thank you so much for listening. I really appreciate it.
Yeah. So thank you so much, Professor Bassett, for this amazing presentation. We will invite you to the upper floor cocktail after, and you'll be able to provide feedback or maybe questions to Professor Bassett, but we will not have them now, even though I have zillions of questions in my mind at this point, because on each slide, the time lapse and advancing in years and age and knowledge of the world must be something that should be interesting to discuss, but we'll discuss this at the comment. So at this point, really, I'd like to congratulate you, and I will invite our colleague, Professor Hélène Giroir, who's Vice Dean at the Faculty of Medicine, not only researcher, but also Vice Dean, and representing the Faculty of Medicine, who will provide Professor Bassett with the award of the Justine Yves Sergent Fund, which is at the Université de Montréal, precisely at the Faculty of Medicine. So maybe you come here.
Yes.
So thanks again for this very exciting presentation. I also have a zillion of questions. So in the name of the Dean and the whole Faculty of Medicine, I would like to extend my congratulations for this very well-deserved prize. I would like also to take the opportunity to thank the Management Committee and the Scientific Committee to make this event possible. Thanks.
Thank you. So, thank you, Hélène, and really the Université de Montréal and faculty is really proud to give you the award, along with a $10,000 award, which comes with the award, so that you can enjoy some of the stuff you've been doing. Thank you so much. So at this point in time, we will stop, and maybe I'll invite Professor Bassett and all of you on the upper floor so that we can have a little bit more discussion, informal discussion. Thank you so much for being here. And thanks for those who are in here.
Everyone on the Zoom, have a beautiful day.